Welcome to Algebra 2. Today we've got section 6.2, the natural base e. All right, so the number e, it's kind of like pi or I. It's one of our famous variables that represent a number, in mathematics. And in this case, e is another irrational number like pi, and it's approximately 2.718. And we refer to it as the natural base because it models growth that is continuous. And then you can see underneath, it's found by taking a slight adjustment to our compound interest formula. If you can remember that was A equals P times 1 plus R over N to the NT power. And what it's doing is it's taking the base of that and working with it. Instead of having n values, we're looking at x values. And then what happens as x approaches infinity? So what we have is this situation where these two places in our compound interest, which represent how frequently that value's compounded per year. So it's telling us things like monthly, daily. You remember that from 6.1, I hope, when we were doing compound interest. Well, here we're looking at what happens if we take that to an infinite number of compounds per year. So it's compounded over and over and over and over and over again. And what we find is that this base turns into this number 2.718. So it shows up all the time in science classes when you talk about elements that decay over time, or bacteria growth, where the population of bacteria is growing exponentially. It models this growth because it's continuously changing. All right, so our base e function, if we take a look at it, it can be used to model growth or decay. You can see that when our base of e is raised to a positive x value, and our inputs are going to be positive, it's showing that growth. And then to get the horizontal flip that we want to see to show decay, it's just that same base of e, but now it's constantly decaying, continuously decaying at that same rate. So now it's a negative rate. It's losing value over time. So how does this change our interest formula? Well, you can see the adjustment right here. This is the other big one for exponential functions: continuous growth. Not monthly, not daily, not weekly, but continuously. We replace that quantity, that 1 plus r over n to the n, we replace that with e to show that it is constantly, continuously growing. It becomes a nice little formula for us to use there. A equals pe to the RT power. All right, so again, just kind of like yesterday, we're going to start working with this number e. Understand that it does mean a number, but it can be incorporated with functions and expressions just like any other exponential term. So we're going to use some of our properties of exponents here. Problem number 6. If I'm going to break this one up, I noticed that 27 over 3, I can simplify that, and then e to the 7th over e to the 4th is being multiplied into numerator and denominator, and we can simplify that. Rules of exponents coming right back into play from chapter 5. 27 over 3 is 9. Then e to the 7th, if I divide out e to the 4th, that becomes e to the 3rd. We subtract the exponents. So there's our simplified expression. And notice there's no x value there, so we could actually type that into a calculator. The calculator has an e key on it, and we could type that in and get a value for it, since e is a number. For number 12 over here, now I'm multiplying all of these terms that have a base of e together, but they have different exponents. So remember that property that says I can show that as the sum of those exponents. And when we combine like terms in that exponential expression that we've got going there, we get 2x plus 7. And we can't simplify it from there, but we have used our properties to make it much simpler to work with. All right, example 2. Tell whether or not this is going to show growth or decay. And again, it just depends on, is that exponent a negative rate included with it or a positive rate included with it. So we'll look at that, and then we will we'll use our calculators to help us make a table of values and graph these functions. So for the first one, number 16, I do notice that it's e to a negative 2 times x power. That is indicating that it has been flipped, and it is now representing decay, because that is showing us the x has been negated. It's a horizontal flip of that graph, whereas a typical e to the x function would grow exponentially. This one has been flipped, so now it falls exponentially. It is modeling decay. And that negative sign tells us all that. All right, now let's graph the function. So we're going to make an XY table of values, and we're just going to type this function in as y1 in our calculator. And yes, we're going to have to work with decimals and maybe round a little bit, but what we should see is we're hoping to see this graph that is falling to show that exponential decay. So in the y equals menu, clear out some stuff that was in there already. The e to the power is along the left-hand side of your calculator. It's the third one up from the bottom. So you have to hit second, and then the key is ln. And we hit that, and it gives us e to some power, and we fill in the power with a negative 2x. And I'm not going to look at the graph. I'm just going to hit second graph to go to the table and pick out some nice points that I know will fit on this coordinate plane. So when I have negative 1 for an x, I get 7.4. And I'm just going to round to the 10th because, you know, human error when we graph this, we can get so close. When x is 0, I should know that one. Y is going to be 1. When x is 1, I get 0.14. And when x is 2, I get 0.018. All right, I know I said I was going to round to the 10th, but let's see what these points look like. Negative 1, I'm up at 7.5-ish. 0, I'm up at 1. At 1, I'm barely up off that x-axis. And at 2, I am sharing some pixels with it. So we notice that it's still a type of exponential function. So it's still going to have that horizontal asymptote. And in this case, they haven't shifted it up or down. So it will still be on the x-axis, or the line y equals 0. And our graph shows that. And we could confirm by looking at the graph as well, but definitely showing exponential decay. Let's look at number 22. Okay, we've got 0.6 times e to the 1/2 x, or 0.5x. Now you'll notice it is raised to a positive number times x in our exponent, so that means there's no horizontal flip involved, so that function is going to show the typical e to the some power that we would anticipate. All right, so we're expecting this to show us growth in our exponential graph, expecting it to look something like this off to the right. And all they've done, if we think about like our parabolic charades that we talked about a long time ago back in September, this is just kind of giving us a vertical shrink, compressing that graph down vertically, and this is saying like half as fast. So it's going to be stretched out horizontally, but it's still going to show that exponential gaining height to the right. So let's type this one in and see if our table agrees with our predictions here. 0.6 e to the 0.5x. And we'll go to our table. Here is what I'm seeing. All right, when x is negative 2, I get a height of 0.22. Negative 1, I'm at 0.36. 0, I'm at 0.6. 1, I'm at 0.98. And 2, I'm at 1.6. And I might put another point or two in there. At 3, we're at 2.7. So we can tell that as our x increases, the y values are starting to separate a little bit more each time. Let's see what it looks like when we put them on the page. Negative 2, we're just off the x-axis. Negative 1, just a touch higher than that. 0, we're just a little over halfway to 1. At 1, almost there. At 2, we're at 1.6. And at 3, we're at 2.7. So we can definitely tell that our graph is rising exponentially. It's just taking it a while because of that vertical shrink and the horizontal stretch. They are really causing that to take a little bit more time to see that exponential growth. but that's all there is to it. Example 3. Well, we're back to rewriting the function, trying to see this 1 plus or minus r to the t power, trying to find a percentage rate of change here. Well, let's take a look at what we're working with here. So for number 28, I've got y equals, and it's 1 times e to the negative 0.75 times t. So I'm going to show that as a power to a power. That's what we definitely used last section and in chapter 5 as well, property of exponents. And let's use our calculator to figure out what that quantity is. What is e to the negative 0.75? So type that in really quick. E to the negative 0.75 power is 0.472. Okay, and remember, there still is that 1 multiplied out front. We don't necessarily need that there. All we're dealing with is the thing to the changing power. But if I wanted to express that as 1 plus or minus something, in this case, it would be 1 minus something. So let's see what that something would be. It would be 1 minus 0.528 to the t power. So this is showing us a decline by 52.8%. So our r is 52.8%, and it is negative, so it's a rate of decay. And that makes sense because we see that negative expressed up here in our exponent. We should know that it's decay. All right, so for number 36, we've got y equals, now that 0.5 is out front, e to the 0.8 to the t power. Let's find out what e to the 0.8 is. It's 2.2255, so 2.226. Okay, just evaluating what's inside that quantity. And if I wanted to express it as 1 plus or minus something inside, that would be 1 plus 1.226. Clearly, this is showing us growth because we're adding on to 1. We are above 100% growth rate here. Our R value is going to be 122.6% for the growth rate. And again, we could tell that by looking at our exponent. It's positive, so we know it's going to show exponential growth. All right, now just kind of in keeping with our idea that E is just a typical exponential graph, we're going to go ahead and make a couple graphs here. They may look familiar. They're definitely the same problems that we did earlier. And all right, example 4, they were the same problems that we had before because I forgot to change them. So for this series of problems, we're going to graph the function with the help of a calculator, either using a table of values or just looking at the graph of the function. And our goal is to identify the domain and range. So I forgot to change the problem numbers. These are problems 32 and 34 in your textbook. And let's just graph these, and let's see if we can't make some predictions first, because, you know, we spent a lot of time this year talking about transformations of functions, and we've already alluded to what's going to happen with regards to our horizontal asymptote in these exponential functions. So in looking at this, I notice that I'm going to have a typical e to the x function, except now, in with the x, I'm adding 1. So I'm anticipating that this graph is shifting left 1 unit. Okay, it's not lifting it up or down at all, so I'm still expecting a horizontal asymptote on the x-axis, or where y equals 0. And it's a positive x for an exponent, so I'm expecting it to show some type of growth like so. So I'm just going to plot a few points from my table of values. Let's see, I've got e to the, and I'm going to make sure x plus 1 is grouped together in parentheses for the exponent. And then if I look at my table, here are the points that I get. So for my x's and y's, I've got at -2, we got 0.37. At -1, I've got 1. At 0, I've got 2.7. And at 2, I've got 20.1. So that one's off the graph for sure, but we kind of expect that. It's exponential growth, people. So -1, 1. 0, I'm up at 2.7, and up at, did I skip over 1? Yeah, at 1, I'm at 7.4. So 1 at 7.4 fits on the screen, then we're way up off of it. So see this? And that makes sense because usually when my input was 0, that meant an exponent of 0 and a height of 1. That has been shifted 1 unit to the left. So it is fitting our transformations so far. Let's look at domain and range. That's what we really want out of this process here. The domain, well, we said for exponential functions, the domain will be all real numbers. And then for the range, let's take a look. Well, I know there's that horizontal asymptote that the graph is being drawn closer and closer to, but it won't reach it. It just gets drawn super duper close to it, but it will never equal that height. So I want all heights that are, well, let's see, my graph is just going up from that asymptote, all heights greater than 0. All right, there's our range. Let's take a look at the second one here, number 34. Charades-wise, I've got a 3 multiplied out front, so I'm thinking, okay, 3 times as tall, vertical stretch, and then x, that -5 grouped in with x. I'm thinking that's going to be a right 5 if it's anything like our other transformations. Let's see what our calculator tells us. Oh, before I do that, no shifting up or down, so I'm still anticipating an asymptote right there on the x-axis, or the line y equals 0. And I don't know, looking at this, it's definitely a positive value on x. They haven't horizontally flipped it, so I'm still expecting to see a growth function that's rising to the right. So let's see, 3 times e to the x minus 5. Type that in. Let's look at our table for my x's and y's. When x equals, and we got some tiny numbers. I'm going to start when x equals 2, I get 0.15. When x equals 4, I'm at 1.1. When x equals 6, I'm at 8.15. And after that, we're off the screen. We've also got some odd ones that we could throw in there. When x is 3, I'm at 0.4. And when x equals 5, I'm at a height of 3. So just to be inclusive of all those points that I can fit on the graph here. So let's see, x equals 2, we are just off of it. 4, or 3, we're at 0.4. At 4, we're at 1.1. At 5, we're up at a height of 3. And at 6, we're up at a height of 8.15. So yeah, hey, we're seeing exponential growth. We're seeing the asymptote at work here. Eventually those x values really start producing some super high heights at the end, and we've got a nice graph. It's following everything that we anticipated. It makes sense. Our domain, just as with all exponentials, is all real numbers. We can plug anything we want into that. And our range, again, all y values that are greater than the height set by the asymptote. All right, just to extend this idea in the notes a little bit, what would change the range? Well, let's imagine that we had, and I'm just going to graph this in red right over top. I hope that's okay. Let's say we had y equals -3e to the x minus 5. What would that do to our range? Well, hopefully we would think that the negative sign out front is a vertical flip. So it would take our graph and flip it vertically, like so, what would that do to our range? Well, now we want all y values that are less than 0 because it's been flipped over the asymptote. We now have all of these heights that are underneath, all the heights that are less than the height of the asymptote. Let's do another one in green over top. What if we had y equals 3e to the x minus 5, and then we, I don't know, added 2 to it afterwards? Well, all that's going to do is it's going to take that blue graph, and that plus 2, we've said that means up 2 units. It's going to shift the whole thing, asymptote included, up 2 units. So we would have a graph that looks kind of like this. What would that do to our range? Well, it would make it so that it's all y values that are greater than, again, it's above this asymptote, but now it's a height of 2 that the asymptote is at. So just a little bit of an indication of how our range may change based on what we see in the function. And again, we're going to go into much further detail with this concept once we get into our transformation section. So don't worry about that now. I just want to kind of explain it well initially. Our final problem. Tritium and sodium-22 decay continuously over time. That's a key word, continuously. That's how we know we're going to use E. In a sample of tritium, the amount Y in milligrams remaining after T years is given by Y equals 10 times E to the negative 0.0562 T. The graph shows the amount of sodium-22 in a sample over time. Which sample started with a greater amount? And which one has a greater amount after 10 years. So we are going to have to do some comparison work between the function for tritium and the graph for sodium-22. Well, let's think. If thinking is always a good idea, right? So part A, which sample started with a greater amount? Well, at the start, that's really saying initially, or when time is 0. So let's see what's happening with our tritium at that point in time. We've got y equals 10 times e to the negative 0.0562 times 0. Well, that's going to be 10 times something to the 0 power. It's just going to be 10 times 1. So we start off with 10 milligrams of tritium. What about the sodium? Well, initially, here, we can read our graph. If this is the t-axis, when time is 0, we have an amount remaining of 15 milligrams. So our sodium, oh boy, this is why we have the periodic table. You can just write Na. Sodium-22, from the graph, the y-intercept, or when t equals 0, it's 15 milligrams. All right, so started with more sodium. More sodium-22 initially. Right. Now, after 10 years, for my tritium, now I'm going to plug in a time value, a t value of 10. So I've got 10 times e to the negative 0.0562 times 10, and see what I get for an output. All right, so I'm just going to type in 10 times e to the, and to multiply by 10, I'm just going to call that negative 0.562. Right, because multiplying by 10 will just kick that decimal point over, and I get 5.7 milligrams. And my sodium, from the graph, I go over to 10. Here I am there. And if I look at the increments, 5, 10, 15, 20, I can tell that I am very, very far below 5 even. So sodium, I'm going to say that's approximately, I don't know, 1.5, 1.5 milligrams. All right, so which has the greater amount after 10 years? There's more tritium after 10 years. Okay, so what's that showing us? That, well, even though we have exponential decay shown in the graph and in the function for the two different elements, because the tritium is decaying at such a slower rate, it starts off with less, but after 10 years, more of it remains than the sodium. Very cool. Like I said, this E value shows up all the time for things decaying over time. History people, they use E values when they determine the dates of artifacts by carbon dating, because they know how carbon decays over time. They can relate things to it. Very, very cool. Very, very applicable. Here is your assignment for section 6.2.